In the last segment, we looked at pH, which is easy when we know what the H plus is. We just take the negative log, push negative, and that's our pH. If we get a base, we get the POH, subtract the POH from 14 and get the pH. Sometimes we don't know what our H plus is, and that's what occurs when we have a weak acid. So we have to write a Ka expression and recognize that for every proton that comes off, we get one conjugate base, that this is a 1-to-1 ratio. So if we define this as question mark, then this becomes question mark. Or if this is X, this is X. So we write our Ka from the table, and I think that this one is 4.4 times 10 to the minus 6. So don't quote me on this. But for the sake of the example, go ahead and use that one. Equals X squared divided by the amount of carbonic acid that we started with, which is right here. We solve for X. X is our H plus. We plug that in, we push log, we push negative, and that's how we get our pH. Okay? Another example that I put on the other side. So a couple of examples there. Okay. Moving forward, we will come back to how we do better than this with buffers. In the meantime, we're going to do a little trip down memory lane and talk about acid-base reactions. Now, the good news here is that this is nothing new. We have seen all these before. The acid-base titration you should have seen already in the prior unit. Remember, acids, the Arrhenius acid is generally the HX or H2X or H3X, something that when you dissociate, put in water, it dissociates to give you an H+. So generally you recognize your simplest acids in this way. Your bases dissolve in water to create an increased concentration of hydroxide. So usually and typically you would look for a hydroxide. Unless, of course, you were looking for Bronsted-Lowry. Nonetheless, H+, Cl-, Na+, OH-, you recognize this as double exchange. So you make some kind of ionic compound called a salt and water. Now, as you know from working throughout the semester, aqueous looks like water. Aqueous looks like water. This particular salt, soluble in water, it's aqueous and it looks like water. Water looks like water. So the question is, how can you see the water forming? How do you know when the reaction is done? Well, you don't. That's rhetorical. So you have to add an indicator. The indicator is something that when you have one drop past neutral will change color. And so an example of that is phenolphthalein. And phenolphthalein will turn pink if there is a slight excess of hydroxide and the solution is basic. So we call that the end point. And the end point is different than equivalence point, because equivalence point is when you create neutral water. Nonetheless, we looked at the math involved in this in the last unit. And so we're going to review how we do this. You put your known means concentration, which is typically molarity, and your unknown goes in the Erlenmeyer flask. And you will continue to add the substance with the known molarity to the unknown until you see a faint color change, which in this instance is pink. And that is when you stop. Okay? Now, as far as the math on this, here are a couple of examples, and we have done these already. What is the molarity of a 30 milliliter sample of phosphoric acid solution? So in this example, the phosphoric acid is the unknown. That is titrated with 18.00 milliliters of 3.00 molar KOH. So the KOH would be out over here, and we would take a V initial, and then we would take a V final. We would subtract the 2, and that's how we get 18.00 milliliters. Nonetheless, you have to start with a balanced equation, and you need your mole ratio. So the mole ratio is 1 mole of acid to 3 moles of base. Okay, you have to have the mole ratio or you cannot calculate this. How will you see the endpoint? With an indicator. How many moles of phosphoric acid are neutralized? Well, the first thing you need to remember is our magic word of. So 18.00 milliliters times 3.00 moles of KOH per liter. So I'm just going to write 1,000 milliliters. And what we're looking for is moles of H3PO4. And so we've talked about this many times. How do you get from moles of one thing to moles of the next? Well, you need the mole ratio. 3 moles to 1 mole. 3 mole KOH, 1 mole H3PO4. Moles of KOH cancel. 3 over 3 cancels, and we end up with 18 divided by 1,000, which is 0.01800 moles of phosphoric acid. Okay, do not drop your significant figures. This is the whole point of the titration. Okay? Of course, we do have 3 sig figs here, so I guess we should drop that. Okay, so the molarity is going to be 0.0180 moles of phosphoric acid divided by the phosphoric acid solution in liters. So we're going to convert that to liters. 0.03000 liters. 1, 2, 3. Okay, so we're good there. Okay, so 0.0180 divided by 0.03000, and we are 0.6, 3 significant figures, molar. Okay? Very good. Okay, here's another example. 10 milliliter sample of HCl of unknown molarity. So that would go here. Our known is the NaOH because we know its molarity. It required 13.50 milliliters of 1.500 molar NaOH to reach endpoint. So we have a V initial, a V final. We subtract those two numbers and we get 13.50. What is the molarity of the HCl? Okay, so the first thing we have to do is the balanced equation. HCl plus NaOH, NaCl, H2O. 1, 1, 1, 1. Molar ratio is 1 to 1. What is the known? The known is the NaOH. What is the unknown? The HCl. What is the mole ratio? 1 to 1. How many moles of acid are neutralized? Start here. 13.50 milliliters. 1.500 moles of NaOH per liter, which is 1,000 milliliters. Moles of NaOH, and what are you looking for? Moles of the acid, which is HCl. Mole ratio is 1 to 1. 1 mole HCl, 1 mole NaOH. Moles of NaOH cancel. Moles of HCl is the unit. So we get out our calculator, 13.50. 13.50 times 1.500 divided by 1,000 is 0.02025. Okay, so I tried that again. I got the same value, so we're going to go with that. The molarity then is 0.02025 divided by the volume in liters. 0.01000. Okay, so I still have this in my calculator. .025 molar. 4 sig figs here, 4 sig figs here, 4 sig figs here. Okay, so you would ask yourself, is that reasonable? Well, that's reasonable. About 2 molar. Dilute, pretty dilute, but certainly not outside the parameters.